Hello teacher, we are group 7 from the course Artificial Intelligence, and today we would like to present our final project on the topic Connect for AI agent using Minimax and AlphaBeta Pruning. Let me introduce you about myself. My name is Nguyễn Thành Đạt and I'm the leader of my group, and my teammate is Phan Thanh Bình and Nguyễn Mạnh Hoàng Gia. Now we will begin with the demonstration of our project. About the table of contents, the first one we will talk about problem and requirement. The next one is the theory that related to the project, and the next part in code explanation. Mr. Nguyễn Mạnh Hoàng Gia will explain the code, and the last part I will show you the gameplay demonstration to help you understand more about our project. So let's start with the first part by my teammate Phan Thanh Bình.
Okay, my name is Phan Thanh Bình, and now I will start with a problem and requirement. Our primary object was to implement an intelligent agent capable of playing against a human or another AI. To achieve this, we utilized the Minimax algorithm optimized with AlphaBeta Pruning. We also focus on three key requirements. The first one is designing a custom heuristic evaluation function to assess both states effectively. Second one is creating a playable interface which uses a GUI for better visualization. And finally, evaluating the AI's performance at different search depths to find the best balance between speed and intelligence. The next one is theory. First, let's quickly review the label rules. Connect 4 is the play on a 7-column by 6-row grid. It uses a gravity-based mechanics. Players take turn dropping a disk and it falls to the lowest available slot. The goal is simple but strategic. Be the first to align 4 pieces horizontally, vertically, or dynamically. If the board fills up with no winner, the game ends in a draw. Why the rules are simple. The math behind is not. The game space is massive with trillions of possible states. This is what we call the branching factor. Look at this exponential growth. At depth 0, we have one state. By depth 2, we have nearly 50 possibilities. And by the depth 4, we have 1,000 of states to evaluate. Because of explosion, we cannot simply solve the game in real time. We typically limit our search to from 4 to 8 moves ahead, which requires a very efficient algorithm. So why do we need an advanced AI techniques? Unlike Tic-Tac-Toe, which is small enough to memorize, Connect 4 has a much larger game tree. To solve this, we need three specific components. The first one is an efficient search algorithm to navigate the tree. The second one is a smart heuristic evaluation to judge positions that aren't wins yet. The final is performance optimization, specifically alpha-beta pruning to handle the computational load. This brings us to our core algorithm, Minimax. The concept is to build a decision tree. The root is the current board. The AI is the max player. It wants to maximize the score, and the opponent is the min player. We assume they play perfectly to minimize our score. The algorithm goes down to the lead nodes. If the AI wins, we give it a huge positive score, about plus 10 billion. And if the opponent wins, a huge negative score. We then backpropagate these values up the tree to choose the best move. However, poor Minimax has a major flaw. It's too slow. Evaluating every single node at depth 8 would require checking over 5.7 million nodes. The solution is alpha-beta pruning. We introduce parameters. The first one is alpha, the best score the max player had its guaranteed so far, and the beta is the maximum score min player guaranteed. The rule is simple. If alpha is greater than or equal beta, we stop. We cut that branch because we already know it won't affect the final decision. Here is our escape time. Imagine we are at the min node. We already found a move worth 5. If we look at the next branch and see a move worth 10, we stop immediately. Why? Because the min player in the opponent would never let us get that 10 if they could force us into 5. And this technique is powerful. In the best case scenario, it can reduce the number of nodes we check by over 99%, allow our AI to search much deeper within the same time limit. Uh, Now let's talk about the brains of the AI, the evaluation function. As I mentioned, we cannot search to the end of the game because it's computationally impossible. We have to stop at the fixed depth, say depth 6, but at depth 6, the game usually unfinishes. No one has won yet. So how does the AI know if it's winning or losing? We need a mathematical formula to quantify the value of these non-terminal states. Uh, Our solution relies on two main strategies. The first one is central control. In Connect 4, the central column is critical because it offers the most potential connections. We give a bonus of 6 points for every piece in the center. The second one is the 4-window evaluation. We scan every window of 4 slots on the board. If we have a 3 pieces and an empty slot, that's a threat. We give 100 points. Crucially, if the opponent has 3 pieces, we give a negative score of 18 points. These penalties force the AI to prioritize defense and block the opponent immediately. Finally, the total score is simply the sum of all window scores plus the central bonus. This approach has significant advantages. First, it is incredibly fast to compute, or one complexity per position. The second one, it captures tactical factors like threat and draft. And finally, it ensures the AI play a side game, balancing aggressive offense with necessary defense. That concludes the theoretical background. Now we will move to the next section, code explanation, is presented by Nguyễn Hoàng Gia.
So in this session, I will explain how our Connect 4 AI is implemented, focusing on the algorithm design, heuristic evaluation, Minimax with AlphaBeta Pruning, and how these components work together in both simulation and GUI gameplay. Let me start with the overall algorithm design. So the game board is represented as a 6 by 7 NumPy 3D array, where 0 means empty, 1 represent player 1 and 2 represent player 2 or the AI. We define the core board operations such as detecting valid moves, dropping piece into a column, checking win conditions, and determining terminal states. So they function from the foundation layer that both the AI and the simulation logic rely on. The turn management is handled explicitly using P1 and P2, which is allow us to reuse the same logic for player vs AI and AI vs AI mode. So this design will keep the system modular and easy to extend. Next, I will explain the heuristic evaluation function, which is critical for AI decision making. Since the Connect 4 has a very large search space, so the AI cannot search until the end of the game. Instead, we evaluate intermediate board states using a custom heuristic function. First, we prioritize the center column. Pieces placed in the middle are more valuable because they participate in more possible winning lines. The board is evaluated using sliding window of 4 consecutive cells across horizontal, vertical, and both diagonal direction. The score strategy is if 4 in a row, then plus 100,000 points is a winning state. If 3 with 1 empty, then plus 1,000. If 2 with 2 empties, then plus 50. And if opponent 3 in a row threat, then minus 1200. This will allow the AI to both build its own threats and block the opponent proactively. The final score is always returned from the AI perspective, so ensuring the consistency in Minimax. Now we'll move on to the next part is the core of the AI, Minimax with AlphaBeta Pruning. So Minimax models the game as a tree of possible future moves. The AI will try to maximize the score, while the opponent will try to minimize it. The algorithm recursively searches until a terminal state is reached or the depth limit is met. Alpha-beta pruning allows us to skip branches that cannot affect the final decision. This dramatically reduces the number of explore nodes. We also sort moves by distance from the center column. This improves pruning efficiency by evaluating stronger moves earlier. When multiple moves have the same score, so we use the weight random tie breaking. This will prevent deterministic behavior and will make the gameplay less repetitive. With the AI logic complete, we support two main gameplay modes. The first one is player vs AI mode. So in this mode, the human inputs a column, the AI will respond using Minimax, and the game will continue until a terminal state. The AI depth is configurable before the game starts, allowing us to test different difficulty levels. In AI vs AI modes, both players are controlled by AI, so this mode is especially useful for performance evaluation. In this mode, we can run multiple games automatically, compare different depths, check win rates and draws. So by running AI vs AI simulation at different depth values, we can clearly observe how such depth affects both game playing strength and performance. Higher depth will allow the AI to reason further ahead and make more optimal decision, but it also increase the computation time. So this is why we use AI vs AI mode, not only for evaluation, but also to experimentally compare intelligence versus efficiency across different depth settings. Learning weights are updated after each AI win, enable adaptive behavior across simulations. As an optional extension, we implement a Tic-Tac-Toe-based GUI to enhance usability. The GUI includes a main menu, player vs AI, and AI vs AI modes, spin boxes for selecting AI depth, and real-time turn indicator. Winning pieces are highlighted visually, improving clarity and user experience. So compared to console-based interaction, this GUI will allow easier demonstration, interactive design, and a more polished presentation. This extension goes beyond the project requirements, but significantly improves the overall quality. And finally, I will briefly introduce several advanced AI enhancements that we added. First, false move detection. This will allow the AI to immediately play winning or blocking moves without running Minimax. The second, randomized tie breaking will avoid predictable gameplay when multiple moves are equally good. Third, the AI update column weights after each win, creating a lightweight learning effect across games. Lastly, moving order and early terminal cutoff significantly reduce search time and improve performance at higher depth. These enhancements demonstrate practical AI optimization beyond the base algorithm. So that's all about the code explanation part. Now let's move on to the demo section.
So far, my teammate has explained the main part of our implementation, including the Minimax algorithm, AlphaBeta pruning, and the heuristic evaluation function, and also playable environment. So this file connect4.py contains the complete source code of our project. It includes the game logic, the AI algorithm, performance logging, and different play mode, such as human versus AI and AI versus AI. Based on the component, our implementation fully satisfies all the project requirements. Now I will run this file to demonstrate how the system works in this practice. So here I execute the program from the command line. So this system allows us to choose between playing against the AI or running AI versus AI experiment. Let me demonstrate the result of this project by playing this game right now. The first one, I run the GUI.py file. And this is the main menu of this game. There are player with a player and AI mode and AI mode. So I will choose the first one is player with AI mode. Let me explain the third step first. The third step defines how many moves ahead the AI will explore using the Minimax algorithm. And in this demo, we mainly use depth 4 and depth 6. Depth 4 is faster but less accurate, while depth 6 is lower but produce stronger and more strategic move. Thanks to AlphaBeta Pruning, the AI can still average deeper level efficiency. And here's the board of this game. This is the game board and it is a 6 by 7 grid represented internally at a two-dimensional array. Each column represents a possible move and the piece fall from the bottom, the column upward, just like in the real game. And the boards use three value 0 for empty cell and 1 for player 1 and 2 for the AI agent. I play as a human player and the AIs use Minimax with AlphaBeta Pruning. I will make a move by selecting a column. Now the AI is calculating the best move. You can see that the AI consider multiple future state and select the move with the highest evaluation score. The AI is not only try to win but also block my potential winning move. And this is demonstrate how the heuristic evaluation guide the AI dimension making process. So AI is winner. I will back to menu to try the AI with AI mode. And this is the AI with AI mode. In this mode, both players are controlled by AI agent. Each AI use the same Minimax algorithm, but play independently. This mode is useful for testing strategy and observing how the AI behave without human input. We can clearly observe patterns such as center, column, preference, and defensive blocking. And we can choose the number of match. So this is the final result. The AI one is winner. So finally, I will run an AI versus AI game with different set depth. The first AI used depth 4, while the second AI used depth 3. So as you can see, the AI1 is winner. The deeper AI generally make a better decision, although it requires more computation time. This comparison highlights the trade-off between performance and decision quality. So this concludes the demonstration of our Connect for AI project. We have shown how Minimax, AlphaBeta Pruning, and heuristic evaluation work together to create an intelligent game playing agent. So about the project outcome, this project we use Minimax search, AlphaBeta Pruning, custom heuristic scoring, and playable Connect for game. Human with AI and AI with AI, performance testing at different depth. So this is the end of our presentation. Thanks for listening.